Let's dive into the hidden world inside our most essential gadgets. We're talking about the microscopic, super high-stakes process of battery welding. This is a world where just one tiny point of failure can mean the difference between having power and, well, not having it. So, let's get right to it.
So think about it. When you picture a high-performance battery, the kind that's powering your phone, your laptop, maybe even an entire electric car, what do you think is actually holding it all together? You might be surprised.
The answer is welds. Not just a few, but thousands of them. Each one a tiny, microscopic connection. And the stakes? They're absolutely astronomical. Just one bad weld can compromise the entire battery pack. We're talking about impacts on performance, safety, and lifespan. It's a huge engineering challenge.
Now, to really get why there are different ways to do this, we first need to understand why these unseen connections are so incredibly important in the first place.
You can think of these welds as the unsung heroes of any battery. They have to do a bunch of things perfectly. They create a reliable electrical highway for all that energy to flow. They provide the physical strength to hold everything together, fighting off vibrations and shocks. And of course, they have a direct say in how well the battery works, how safe it is, and ultimately, how long it's going to last.
All right, so let's meet our first contender in this welding showdown, ultrasonic welding. This technique is fascinating because it actually joins metals together without melting them.
How is that even possible, right? Well, imagine rubbing your hands together really fast to create heat. Ultrasonic welding is kind of like that, but on a microscopic level. It uses these super high-frequency vibrations to literally scrub two pieces of metal together under pressure, and that creates a really strong molecular bond. It's what's called a solid-state process, and that is a total game-changer.
And this method really shines in its results. Because it doesn't melt the metal, the electrical resistance at the joint is incredibly low and super consistent, and that's a huge deal for battery efficiency. It makes it absolutely perfect for joining delicate, different materials, like the thin copper and aluminum foils you find deep inside battery cells, all without causing any heat damage.
Okay, let's move on to our next technique. This is the high-tech, high-speed option. Think of laser welding as a surgical tool for building batteries. So unlike the friction method we just saw, a laser uses a highly focused beam of light to melt and fuse the materials. It's a non-contact process, which means nothing physically touches the weld point except pure energy. And this allows for unbelievable speed and precision, creating what they call a tiny heat-affected zone. What does that get you? Well, the laser welds are incredibly strong, which makes them perfect for thicker components, like the battery terminals and bus bars. That precision means there's minimal heat damage to any of the sensitive parts nearby, which gives you fantastic structural reliability. Its speed and accuracy make it the go-to for high-volume production, like what you'd see in EV battery factories. And finally, our third technique, resistance welding. This is the established, powerful workhorse of the industry. It's been around for a long time and for a very good reason.
The idea here is actually pretty simple, but it's really powerful. Think of the glowing filament inside an old light bulb or a toaster. Resistance welding does something similar. It passes a huge electrical current through two pieces of metal. Their own natural resistance to that current generates intense heat right where they touch, melting them together to form the weld.
But here's the trade-off. While it's a mature, reliable process that makes strong welds, it is way less precise than a laser. The quality can be a little inconsistent if it's not perfectly controlled, and the process can actually leave a little dint from the electrodes. It's a powerful tool for sure, but it's more of a sledgehammer than a scalpel.
And this comparison really gets to the heart of it. Laser welding is a surgical strike. Minimal heat bleeds into the surrounding areas. Resistance welding, on the other hand, is much more of a blunt instrument, creating a much larger heat-affected zone. And that difference is absolutely critical when you're working just millimeters away from a battery's sensitive internal chemistry.
So, after seeing our three contenders, who's the winner? Well, the truth is, there's no single champion here. It's all about choosing the right tool for the right job.
See, the choice always comes down to the specific application. If you're bonding those delicate, thin foils without melting them, you choose ultrasonic. If you're running a high-speed, automated production line that requires pinpoint accuracy, laser is your champion. And if you're working with thicker, less sensitive parts where raw power is the most important thing, the good old workhorse of resistance welding gets the call.
And just to put the demand for perfection into perspective, for a modern battery pack to be considered reliable,
The success rate of these thousands of tiny little welds needs to be greater than 99.9%. There is almost zero room for error.
So, the next time you pick up your phone, or maybe hop in an electric car, just remember the invisible engineering that's holding it all together. These hidden connections, these microscopic welds, they are truly the unsung heroes that are powering our modern world.
And that kind of leaves us with a final thought. As we all keep pushing for batteries that are more powerful, that last longer, and are even safer, the pressure to create that perfect connection is only going to grow. What new innovations in welding technology will get us there? It's a connection worth watching.